In this lesson, we'll talk about t-tests in SAS. I'm going to start by giving a brief, very quick and brief overview of t-statistic, remind people what it is, and then we'll quickly move into some examples of how to get t-statistics and perform t-tests using SAS. So again, if you have a substantial background in statistics, the introductory part will probably not be of much use to you, and you might want to skip through a little bit to the actual applied section of this lesson. A t-statistic essentially is really a ratio, and it's a ratio in the numerator that has a difference between some estimated observed value of a parameter and the hypothesized value, and in the denominator you generally have a standard error. Okay? And the t-statistic can be derived from many different statistics. It's commonly derived from sample means, and it's used to compare observed means to some hypothesized means. So we'll talk about one sample t-test in this lesson, and an example there might be if you're collecting a sample of 100 people out of a larger population of maybe 1 million, whatever the actual population you want to make inference about, whatever that population size might be. We'll assume you're taking a smaller sample, a much smaller sample of maybe 100, and you're measuring blood pressures, and maybe you want to make inference about what the actual mean blood pressure is in that population, and you may have a hypothesis about what the mean could be. So maybe you hypothesize a mean blood pressure of 120 millimeters of mercury, and then you'll compare the observed mean in your sample to that hypothesized mean and see what the evidence is that the mean is different or the same. And then we'll go on and we'll extend this thinking into the context of two-sample t-tests, and we'll also talk briefly about paired t-tests. Now, a very important part of the t-test, of course, is the denominator, and in the denominator we have the standard deviation of a sampling mean. We're talking about sample means, and we generally refer to that as the standard error because it's an unknown quantity, and this is characterized as the standard deviation of whatever the variable is you're measuring divided by the square root of n, and that would give you the standard error. So standard error of the sampling mean is effectively a measure of the variability of your sampling distribution, or in other words, if you have that population of 1 million people and you can only sample 100 to try and estimate the mean, if you were to resample 100 individuals over and over and over again, the mean value you obtain would vary. And the standard error helps give a sense of how variable that would be, and in turn gives us a sense of how close to the true population mean your sample estimate might be. I always think it's useful at this point to just think for a moment about why mean and standard deviations are so commonly used to describe data. And the reason is that the mean and the standard deviation, or the standard error, substituting for the standard deviation of a sampling mean, these two statistics entirely characterize the normal distribution, and the normal distribution is an incredibly common probability distribution that is used to help us make inference in statistics. And this is relevant to t-tests and t-statistics because a t-distribution also is entirely characterized by the mean and the standard error of a sample. And as the sample size gets infinitely large, the t-distribution will approximate the normal distribution. So based on means and standard errors, essentially we can derive some inference about the probability of observing some particular value, a mean blood pressure from a sample, given some a priori hypothesized value. So with that in mind, and I apologize for the very quick and crude overview, One of the assumptions is that most people will have been introduced to a t-statistic at some point in the past, but quite often I found in this course that people have not dealt with the statistic very recently, so it's helpful to quickly provide some background and a few reminders as we move into the applied portion of it. So moving forward now, we're going to talk about the t-test procedure in SAS. We'll see examples of how to calculate a one-sample t-test, a two-sample t-test, and a paired t-test. 3 different t-tests that are appropriate in different contexts. But no matter what t-test you're running, it's important to remember that the dependent variable should be continuous in nature, and generally it should be normally distributed. So we'll start with the one-sample t-test, and the one-sample t-test compares the mean value of a variable to some hypothesized null value. For example, here we're getting a t-statistic, which is defined by the observed mean. So we could think of this as the observed mean blood pressure from our sample, subtracting off some hypothesized true mean of the larger population that we don't know, but we make a guess at, and then divided by the standard error, or standard deviation of the mean divided by the square root of n. So for example, we can think about blood pressures in our population that we've been using throughout this course, and we might wonder whether or not the mean blood pressure of that population is different than 120 millimeters of mercury. So to state sort of a classic statistical null hypothesis, we would be hypothesizing that the mean systolic blood pressure is equal to 120, and then we'll see if there's evidence in the data to reject that null, suggesting that maybe the systolic blood pressure is different than 120. Similarly, we could think about mean BMI and hypothesize whether or not mean BMI is equal to 25 or different than 25. And this is an example of the t-test procedure that will perform one-sample t-tests. As is usually the case, this is a procedure, so we start with proc. T-test is the name of the procedure we specify, and then you specify the input data set that holds the variables of interest. Then you'll have a var statement, and in the var statement you simply specify the continuous variables for which you want to calculate a one-sample t-test. And by default in SAS you will get a comparison to 0. In other words, the hypothesized value, or true value in the larger population, is going to be 0. Now if you wanted to change that null hypothesis, you simply need to add a very quick option to the proc t-test statement, and you would specify HO equals whatever your hypothesized mean value is. So in this case, we want to see whether or not the observed blood pressure is different than a hypothesized mean blood pressure of 120. So I'm simply adding in HO, this is H0, the number 0, equals 120. And nothing else in the code changes. And then similarly, you could also change the alpha, which will change the type 1 error rate, and that's done simply by specifying alpha equals whatever alpha you choose. The default in SAS is 0.05, so in this example we would be changing it to 0.01. And what this really changes in the output, as we'll see, is the confidence intervals. By specifying alpha equals 0.01, we will now have 99% confidence intervals as opposed to 95% confidence intervals. So here are 2 examples of the t-test where I've added a few options, and in these situations I'm only considering systolic blood pressure in these 2 procedures. Obviously it wouldn't make much sense to add BMI to this particular t-test procedure because the null hypothesis is 120, and that's really no better than a value of 0 for BMI. So here are 2 more t-tests that are focused on BMI. In the first example, we're changing the null hypothesis to be a value of 25, and we're changing the alpha again to 0.01 in this particular t-test. And if we wanted, we could add both options in one line. So we could add HO equal 25 and alpha equal 0.01 if we wanted to specify both of those options within one t-test. That's also a possibility. Now let's go over into the SAS editor file for this lesson and see what it looks like. So I will highlight my libname statement and my data step to create an analytical data set. Ran fine. And then I'll just start with the basic t-test. The first example we saw on the slides, a little bit bigger, where we're getting one sample t-test for systolic blood pressure and BMI. And again, in this example, without specifying any additional options, the null against which the observed values will be tested are both 0. So we're assuming mean systolic blood pressure of 0 and mean BMI of 0, which is not very realistic, but for the purpose of seeing some output to get started, we'll take a look at that. Before we do that, I'm actually going to remove a title. As you saw in the previous output, there was a title that was left over from a previous example prior to this lesson. So I'll just type in a title statement and leave it blank, and that will delete the title from the output. We can rerun that. So here's the output, starting with systolic blood pressure. 12,724 observations were included in this calculation. The mean value is 133. Here you get the standard deviation and the standard error of that mean, minimum and maximum values. And then below we have the t-value. So this gives us the t-statistic, and it's an enormous t-statistic, 611, and the p-value corresponding to that t-value is less than 0.0001. Okay? So since we were comparing to such an extreme null, a systolic blood pressure of 0, clearly our population mean is much different than 0, which can be seen in the enormous t-value and the low p-value. And if you wanted to calculate this t-statistic, you would simply take 133 minus 0, which is equal to 133, of course, and divide by the standard error. And that will give you a value of 611. And then below we have the output for BMI. So mean BMI is 25. Standard deviation and standard error are presented. And again, the t-value is quite large. It's clearly the mean BMI in the population. The true population is not 0, and that's reflected in this large p-value, and again, very small p-value. Now we can move on and show some of the examples where we added some options. These are very similar to the examples I showed in the slides. So first, we're running a t-test on the input dataset work.master. We're specifying a null hypothesis of a mean blood pressure equal to 120. And then we specify in the var statement the variable of interest, which again, of course, is systolic blood pressure. So now again, we see that the mean is still the same. Nothing has changed there. It's still the same 12,724 individuals, and the standard deviation and standard error are still the same, but the t-value now is much, much smaller, but still quite large. It's a t-value of 60 and a p-value corresponding to that t-value, which is very, very low. So in other words, we can reject the null hypothesis that mean blood pressure in this population is 120 and instead accept an alternative hypothesis that the mean blood pressure is something different. And if you wanted to calculate this t-statistic by hand, you'd simply take the difference between 133 and the hypothesized value of 120. So that would be 13, and divide by the standard error of 0.21, and that will give you approximately 60. And you can note here the 95% confidence limits on the mean, 132.7 to 133.5, and we can compare that to the 99% confidence limits if we modify the alpha equals option. So here again, in this next procedure, starting in line 188, we're setting the type 1 error rate, or the alpha, equal to 0.01, and that will give us 99% confidence intervals. And also note that I'm changing the null value from 120 to 128 to see if there's evidence to reject the null that blood pressure is different than 128 in this example. So again, the mean is unchanged. The only thing that will change here in comparison to the previous output is the t-value, which is now 23, and again that's derived by 133 minus 128 divided by the standard error, so we still have a very large t-value, which is highly statistically significant, indicated by the very low p-value here. Another thing that has changed, of course, is the 95% we have 99% confidence limits now instead of 95% confidence limits. But due to rounding, they actually, in this example, appear to be identical. And then you could go forward and also do the same thing for BMI using different options. Now we'll move on to two-sample t-test. And with the two-sample t-test, the goal of the inference is to compare means between two independent groups. And in the context of epidemiology, usually those groups are defined by some exposure of interest or some treatment of interest, depending on your study design. So for example, if we're interested in the relationship between body composition and systolic blood pressure, we could create a variable that corresponds to being normal weight or overweight, and then compare mean systolic blood pressures among individuals in our study who are normal weight and overweight. And the formula is given here. We're simply taking the difference between the two means and the two groups, and we're seeing whether or not that difference is different than some hypothesized value. And usually in the two-sample setting, the hypothesized value is assumed to be 0, because you simply want to see whether or not the two groups are different. And the standard deviation is calculated as shown in the formula below, based on pooled standard deviations for both for the outcome variable in both groups. Now, an important thing to be aware of in the context of two-sample t-tests is to make sure that the groups are independent. This means that the values of the outcome variable should be completely unrelated between the two groups. In other words, an individual's blood pressure in group 1 should in no way, shape, or form influence an individual's blood pressure who occurs in group 2. And that's generally true if individuals in each group are not the same. That's not always true. There are certain designs where that won't hold, but commonly, as long as you don't have individuals who are resampled many times and therefore appear in both comparison groups, the groups will likely be independent. And here are a couple of common examples of other exposure variables that might be used in epidemiological settings. You might look at smokers versus non-smokers and see if levels of some outcome variable are different, or people with high versus low education, or high versus low cholesterol. So, as I alluded to in the previous slide, a common situation when the groups are not independent would be in pre-post intervention studies. If you wanted to think about weight loss during an intervention, and you compared the mean weight of individuals at baseline to the mean weight of individuals at the follow-up examination, and the individuals in both groups then are of course the same because you're measuring weights before and after an intervention, those two groups are not independent. The weight at baseline of an individual will be highly correlated in many settings to the weight of the individual when they come back for their follow-up. So just be aware that settings like this are not appropriate for a two-sample t-test. As we said, the two-sample t-test compares the mean value of some continuous outcome variable between two levels of a categorical or exposure variable. And here's what it would look like in SAS. So we're again using the t-test procedure, so we specify proc t-test in our data set. And the major difference here as compared to the one sample setting is that we're adding a class statement, and in the class statement you need to specify the two-level explanatory variable, or in other words exposure variable, of interest. And then again in the var statement you specify the dependent variable or the outcome of interest. In this example we're going to look at whether or not systolic blood pressure, the mean values of systolic blood pressure, vary according to levels of the overweight variable. And overweight is simply defined as being normal weight versus overweight, and again it's a two-level variable. There are only two possible values that a participant can have in the data set. And this next example shows the same t-test, but here we're going to instead hypothesize, instead of the default null value of 0, we're going to hypothesize a value of 13. In other words, we want to know whether or not the difference in mean systolic blood pressure between normal weight and underweight individuals is equal to 13 or different than 13. And I'm also going to use an order equal formatted option in that second example. So this just demonstrates again how you can specify multiple options to various statements. And this particular option is going to help format the output in a way that will make it a bit more readable, but it will also help in terms of making sure that the correct calculations are done by SAS. And I'll show an example of that in the actual editor file. So let's jump over to the editor file now, scroll down, and talk about the two-sample t-test. So this is the code that we had talked about in the slides. And in this first example, we're running a two-sample t-test that will look at variation in mean systolic blood pressure according to levels of the variable overweight, which is specified in the class statement. And then I've also added a format simply to help with the readability of the output. If you're interested in knowing the rules of this format exposed f that I'm applying to the overweight variable, you could scroll up in this code and take a look at the proc format above. So here's the output, and the formats are printing out. So I have not exposed and exposed, which I'm considering as being underweight individual, or excuse me, normal weight individuals are considered not exposed, and the overweight individuals and also the obese are included in this group are the exposed. This gives the sample size in each group. Here are the mean systolic blood pressures and the difference between the mean. And note that this difference is negative, and that's negative simply because SAS ordered these two variables, the levels of the overweight variable, so that the not exposed was first and the exposed was second. So you end up getting a negative value here. We'll talk more about that in a minute, but that is important under certain circumstances. And then again you have standard deviations for each group, and also for the difference in the means and the standard error. And here are the t-values that you can use to determine whether or not the difference is 0 or different than 0. So our null hypothesis is that the difference in the means is 0, and what we're observing is that the difference is actually about 13. If you want to determine which variance to use, you can use the equality of variances information below. In large sample sizes, oftentimes the t-values will be very similar and it's fairly irrelevant which you use, but to be technically correct, SAS by default provides information on equality of variances where it does a statistical test to determine whether or not the variance of the mean is the same in each level of the exposure variable. In this case, overweight is the exposure variable. And we see here from a very low p-value that the null hypothesis that the variances are equal can be rejected, and instead we go with the alternative hypothesis, which is that the variances are unequal. So based on that, then we simply look to the unequal variances t-value, 31.08, and the p value for that t statistic is quite low, certainly less than p equal 0.05, so we would reject the null hypothesis that mean systolic blood pressures are the same in the two groups, or in other words, the difference between mean systolic blood pressure in the two groups of individuals defined as normal weight versus overweight is different than 0. So let's move on to a second example, and in this second example I'm going to change the hypothesized difference from 0, which is the default in SAS, to 13. So I want to test whether or not the differences in mean systolic blood pressure are equal to 13 or different than 13. And I'm going to use this order equal formatted option. And I'll show you how that impacts the results in 1 second. So very similar output to what we had before. A key difference is that because I use the order equal formatted, SAS will order the exposure variable, or the variable in the classification statement, alphabetically according to the format that was applied to it. Or in other words, because E comes before N, the exposed will be first and the non-exposed will be second, and as a result we'll get a positive 13 instead of a negative 13. Now that's very important because this value, when you're changing the null against which you're testing, we changed it from a value of 0 to a value of 13. This is the value that will be used in the numerator of the calculation of the t-statistic. So we'll have a value of 13 subtracting of 13.13, subtracting away a value of 13, which was our null, divided by the standard error, and that gives us a very small t-value and a very high p-value, no matter which t-statistic we would use. So we can conclude that based on these data, there's no evidence to reject the null hypothesis that the difference in the mean systolic blood pressures between the two groups is equal to 13. But we stick with the null, and that's how you would interpret this output. If we were to run the exact same code with one exception, we remove the order equal formatted. So down below I've removed the order equal formatted option. Now what happens is, again, we have this negative 13. So the calculation of the t-statistic in the eyes of SAS is going to be negative 13 minus 13, which will give you something like negative 26, divided by the standard error, 0.42, is going to give you a t-value of approximately 60. And this will be deemed to be highly statistically significant. So in effect, what we're really interested in is whether or not the absolute difference between the two groups is 13. But because of the way SAS is programmed, it's not thinking in those terms, and therefore it's very careful to make sure that you structure the output in a way such that the sign of the difference is appropriate for the hypothesis test that you're making. In this example, we would reject the null hypothesis that the difference in mean systolic blood pressure is equal to 13, when in fact it seems that the difference is equal to 13. And here I've provided more code if you wanted to consider relationships between other variables in the data set and either blood pressure or BMI. In these two different examples, you're looking at whether or not blood pressure differs by gender or whether BMI differs by gender. I'll let you run that on your own. Or alternatively, maybe you want to look at the relationship between age and blood pressure and age and BMI. So a quick way to do that may be in the context of age, since we have a continuous age variable, and that's our explanatory variable, we have to somehow reoperationalize age into a two-level dichotomous variable. A quick way to think about doing that might be to run a univariate on the variable age. And I'll just take the median value. I can find it here quickly, which is 44. And now I bring that information back into my SAS code, and I created a data step that will create a new output SAS data set named work.master2, starting from an input data set work.master, and using some simple if-then statements, I created a variable age q2, which has a value of 0 if age is less than or equal to 44, which was the median, and it has a value of 1 if age is greater than the median value of 44. And similarly, I used information from the proc univariate output to determine what the 75th percentile of age was, and I'm creating a new categorical variable, age 75th, which is equal to 0 and 1, according to whether or not the original age variable is less than or greater than equal to the 75th percentile. So we could run that data step and then maybe run a proc freak to look at the results and make sure everything looks okay. So again here, I have a roughly 50-50 split of individuals above and below the median of age, as we should. It's not perfect because there may be some ties right at the median. And then about 3,388 individuals, almost 27%, are above the 75th percentile. Again, it won't come out exactly perfect if there are some ties around the 75th percentile. And then about 73% are below the 75th percentile. The main point here is that now we have two different age variables defined in different ways that have two levels. And as a result, we can use them in a proc t-test. Oh, forgot to show the output for the second proc freak, so I'll just quickly run that. So all this was doing is showing the cross-tabulation of the HQ2 values with the original age values. So we could just check here and see that everybody 44 and less has a value of 0, the first half of this output, and then once the ages go into the 45 range, everybody has a value of 1 for age Q2, which is what we had intended. That's just a double check to make sure our coding worked correctly. And then you simply run a t-test, and now we're putting the age Q2 variable into the class statement, and we have the systolic blood pressure variable in the var statement. So we see when comparing people below versus above the median age, systolic blood pressures are 121 versus 145. And if we just ignore the sign and think about this in absolute terms, because what we were really interested in here was whether or not they were different, or in other words, is the difference different than 0, we see there's strong evidence for that. So 23 minus the hypothesized value of 0 divided by the standard error will give us these t-values, and regardless of which t-value we use, this is a highly statistically significant result. So we can reject the null hypothesis that mean systolic blood pressure is equal between these two age groups and accept the alternative hypothesis that mean systolic blood pressures are different. And I've provided some additional examples here that you could work through if you were interested in, but I'll skip over a few of them. I do want to talk again about using formats. So another approach to thinking about and two-level age variable, and to get that set up correctly so that it would work within the context of a proc t-test would be to use a format. So here I'm just using a proc format to create a new age form, or excuse me, a new format that I plan to apply to the age variable. I'm naming the new format med age f, and the rules of the format are simply saying values in the range of 20 to 43 should be grouped together under this title, 20 to 43, and 44 to high will be assigned this format label, 44 to high, and as a result they'll all be grouped together under this title or label. So I would highlight that, and then I'll also run a quick proc freak. Within the proc freak I need to remember to apply the format to the variable I want it used for, age in this situation, and I'll just double check that the output looks reasonable and that there weren't any mistakes in creating the format. So here you see there are 6,327 individuals who are in the age range 20 to 43 and 6,397 in the age range 44 to high. And again, these are simply the formats that we applied based on the format created here. And now you can run a proc t-test as we have before. You can actually specify your continuous age variable in the class statement, but it's very important that you also include the format statement. The format statement is going to allow SAS to view the age variable essentially as a two-level categorical variable. Even though it's not changing the original values of the age variable, because we're applying this format, and the format effectively divides people into two separate groups, the t-test will work, and you can look at mean systolic blood pressure by age in this example. Okay. So you're comparing 20 to 43-year-olds to 44 and above. And the results are similar to what we saw in the previous example. I've summarized the output and some interpretation just so you have it in your notes. And we discussed the two-sample t-test equality of variances. And this just outlines again the steps you would go through to determine, based on the SAS output, which t-value and p-value should be interpreted. The key issue here, or the key point, is that in the equality of variances output, the null hypothesis is that the variances are equal. So if you have a p-value less than, say, 0.05, then you can reject that and you conclude variances are not equal, and then you would use the Satterthwaite t-statistic. So now let's finish by talking about paired t-tests. A paired t-test will compare means of continuous variables between two levels of a categorical variable, and it's used when the observations in the two groups, or the two levels of the categorical variable, are not independent of one another. So a very frequent example where this occurs, as we discussed previously, is when you're measuring the same individuals twice. So we've been using this very small data set with an example of a weight loss study where participants have a baseline weight or a start weight, and then they come back and they have some end weight. And if we just simply wanted to say, is there evidence that people in this study, regardless of their treatment, but all of the participants in the study, if you look at their weight loss, is it different than zero? In other words, did they lose or gain weight? You could use a paired t-test in this particular setting. So here's some SAS code that I've put in the editor file that will generate a quick small data set. We've seen this data set before. And the new code here is the paired t-test code. This is still the t-test procedure, so you specify a proc t-test in the data set you want to run the t-test on. Here we're going to run it on work.club1, which is being created up above in this code. And for a paired t-test, you need to specify a paired statement. And in the paired statement, you cross-tabulate the two variables of interest connected with an asterisk. So these variables actually correspond to the actual continuous variable that you want to assess change in. So here you have to make sure that your data set is structured such that you have one variable that will correspond to the start weight and one variable that will correspond to the end weight. So this is one of an example, and there are many of them when you're analyzing data in SAS, where you have to structure the data in a particular way given the question that's being asked. So in the data set, as you'll see up above, start weight and end weight for each observation are in the same row. Okay? So for example, David here has a start weight of 189 and an end weight of 165, and these two weights are in the same row as opposed to being two separate rows in the data set, one corresponding to the first study visit and the second corresponding to the second visit. And before we go into SAS and do this, I want to show an alternate approach to generating the data set and running a t-test that would be inappropriate. So this data set now structures the data such that each study visit is one row in the data set. So for example, this the first row of the data set will correspond to David. He has a start weight of 189, and the last variable in the data set is time. So this is time 1, and you see for the first several observations we're inputting their time 1 value, and then all of the participants are again input, constituting an additional row in the data set for each individual, corresponding to their time 2, or in other words, their end weight. So given this data structure, we just have one variable for the weights, which is weight, and we have a second variable corresponding to time. Now, some people may consider the option of running a paired t-test where you simply look at whether or not weight is different by time. But as you'll see, you get the wrong answer when you do this, because this particular t-test procedure in SAS does not take into consideration any possible correlation of the outcome variable according to level of the categorical variable. It's going to assume that it's independent and do the calculations accordingly. And we know, because based on our background knowledge of this data set, that the start weights and the end weights are not independent. So let's go into SAS and just take a quick look. So I'll generate that first data set and just print the data set to the output window so we can take a look. So you see that each observation fills one row of the data set, and they have a different variable for the start weight and a different variable for the end weight. And here I'm going to run the paired t-test on the dataset club 1. I'm excluding one participant who did not have both a start weight and an end weight so that we can have a constant sample size throughout these examples. And I'm using the paired statement that will compare mean start weight to mean end weight. And it will do so assuming that this is a paired design, or in other words, it will account for the correlation between the first and second weight measurements. And when we do that, we have 5 individuals included. The mean difference between the start weight and the end weight is 17.8. You get the standard deviation and the standard error, the minimum and the maximum. And if you take 17.8 divided by the standard error, you get a t-value of 7 and a p-value of 0.002. So we would reject the null hypothesis that the difference between start weight and end weight is 0, and we can accept the alternative that those weights are different, and in fact people appear to have lost on average about 17.8 pounds in this study. I'm going to use really quickly a proc core here, which will give us a correlation between two variables, simply to show you that there is a correlation in this data set between start weight and end weight, and the correlation is very strong. So start weight and end weight are correlated 0.99. So in other words, the weight at the first study visit is highly predictive of and related to the weight at the second visit. So the two groups are not independent, and because of this, if you try and run a two-sample t-test, which we'll do below, you'll get an answer that's very different from the paired t-test we ran above. Now, this again is just the SAS code to generate the data set in a different structure. This is a long form, and again, each participant will appear twice in this data set. They will comprise, or they will have two separate rows in the data set for each individual participant, one row corresponding to the visit 1 and one row corresponding to visit 2. And then based on that, I'll run a two-sample t-test, which again is inappropriate in this context, where I specify the classification variable to be time and the outcome variable to be weight. In other words, is weight different across time? And this is going to assume complete independence between the two groups. So when we do that, we again have 5 individuals at each time point. The same individuals measured 2 different times. The mean weights are given here, and again the difference is 17.8, exactly what we saw from the paired t-test. But here the standard error of the difference is 21. It's much larger than what we observed for the paired t-test. And as a result, 17.8 divided by 21 gives you a t-value of 0.83, and this is not even close to being statistically significant. So by using the wrong method and applying it to the exact same data, you end up with 2 very different answers. So the key difference between the output for the 2 different t-tests that explains those divergent results was the standard error. In the paired t-test setting, we had a standard error of 2.5, which yielded a t-value of 7, and in the two-sample t-test, our standard error was 21.5, which gave us a t-value of 0.8. So again, standard errors are very different, and that's because there's correlation between the variables, which influences the variance of the difference. That's beyond the scope of this class, and we won't go into great detail, but if you're interested in, as a quick reminder, the variance of a difference is equal to the sum of the variances, subtracting off 2 times the covariance, which simply means that if there's covariance or correlation between the 2 groups, or the mean values of your outcome variable between the 2 groups, the actual variance and then therefore the standard error will be lower. And the two-sample t-test in SAS does not account for the possibility of covariance or correlation between the variables, whereas the paired t-test does. Now, all that being said, it would still be appropriate to compare mean weight change between the 2 groups, the treatment versus control, or the teams, red versus yellow, using a two-sample t-test, because the individuals in each group would be different. Because each individual is randomized to be in one group, and therefore you could look at their weight change value according to treatment group, and that would be legitimate. So in summary, we've talked about the t-test overall. We went over specific examples of a one-sample t-test, a two-sample t-test, and paired t-tests. I tried to give some general examples of when each would be appropriate, and you've seen some code demonstrating how these various t-tests can be run.